This video will begin our discussion of spherical coordinates. Spherical is a 3D coordinate system. Dealt with mostly, why they call it a sphere is it creates a type of sphere. So we have three measurements here. We have the point, it's written down, but I'm going to write it, rho. We have theta, and we have phi. Okay, so what each thing is rho, the p there, rho. All right, let me write that out, rho. Okay, rho, I think that's how you spell it. Correct. Forgive me if it's wrong. Correct me in an email if it's not. Okay, rho. What rho does, this is how I think about it. Rho determines a radius for a sphere. So I think about it that way. So if I said, okay, rho was 3 of my coordinate system, I'm going to think of a sphere with radius 3. I know whatever point I'm about to plot will be on that sphere of radius 3. What theta does, theta is like your latitude, I think. Latitude, your equator type thing. So it will determine, once we have your P, your surface, this will determine like your flat angle turn of like your equator, right? From the x-axis over to wherever we're at, wherever your point is. So rho determines like the size of the sphere. I'm going to have a sphere with a radius of whatever. Theta will decide how much from the x-axis, so this is like on the equator, how much will it turn on the equator. And then phi is the last one, and this is the angle from the North Pole down. So on your sphere, it'd be like your North Pole, and then if I had a 30-degree angle, I would drop down 30 degrees from the North Pole in this way, right? Positive going down. All right, couple things here that isn't mentioned in my notes. I wrote them in. Phi is always between 0 and pi. It'll never be past that. Okay, pi is the South Pole. So 0, phi would be the North Pole. If I go down pi degrees all the way down, right, that would be my South Pole. Also, rho will always be positive. It's just because we can actually get, it makes it more of a function if I can do that. Meaning I'm not going to have multiple rows that give me the same spot like we can in polar. All right, so I hope that makes sense. If it doesn't, I would totally recommend you Googling and looking up YouTube videos of spherical coordinates. Just that, no calculus. We'll be doing the calculus over it. It's going to be hard to kind of think about, maybe if you don't understand it, but I'm going to show you a couple of ways to project them and understand it. But if you'd really like your grasp of spherical to be great, maybe go check out a video of spherical coordinates. Somebody would be able to project it onto something pretty, like an animation, and show you exactly how those work. One thing I want to mention is rho and r are not the same thing. Rho is the radius of that sphere. It's the same always around it, right? R is the distance on the equator. Right? It's actually the projection of rho down onto the xy plane. So there is a weird relationship there. We have a couple formulas. Okay, so here is the xyz, just switching them. If I have rho and I have phi and I have cosine, notice that these are very similar to cylindrical, except for it adds in, instead of an r, it uses a p, and then it adds in these signs here. Oh, I see a typo. Let me go ahead and fix this for you. This is not cosine. This is sine theta. Your notes will be fixed. Mine were off. I'm going to pull up that page right now, and so I'll remember it. Great. All right. Thank you for being patient. Okay. So we have that. That's sine. That's just like r sine for y. X is our cosine, right? But we change them to rows, and then we add that sine phi in. Z is also definitely different in this case. It's rho cosine phi. And then we have a couple other things that are going to help us out quite a bit. This one in particular, x squared plus y squared plus z squared is going to be rho squared. You can probably imagine the problems we've done in the past where that would have helped us out, because we're taking 3 variables down to 1. We also can convert r using what's there. R equals rho sine phi. Now, what is this going to look like when we convert it? All right, so the first one, it will still be the theta. We always want that outside. Then it's going to be phi, and then r. All right, and then when we plug this in, I'm going to cheat here. This is going to be the x that's up here. I would plug that in. I'd plug in y, that's right here. And then z, which is right here. So if you want to write that in, if you have the room, my handwriting is just too sloppy. For cylindrical and polar, we would add this R. Well, spherical has its own thing. It's a little more complicated. You're going to add a rho squared sine phi. That is the same thing as the R. What this is called is it's called the Jacobian. If you'd like to check that out. Depending on what semester you take me with, we'll do this section. If not, it will be a supplemental section, just depending on the nature of our semester. But this is called the Jacobian. The same thing with R and polar. It's called the Jacobian. There's a whole section that's after this one that is focused on that. Okay, and then I just put in the dr, d phi, d theta. So the big kicker here, the r that people mess up here, will be remembering that. Throw that into every integral that you switch to spherical, you have to put that in. All right, let's get an example under our belt. So they want us to evaluate this. Remember, it's not exactly volume. I have triple integral of that, square root of x squared plus y squared plus z squared. And then the region they want us to do it over is the sphere. So this is the solid sphere, because that less than or equal to. And it has a radius of square root of 3. Okay, so I'm going to give you some notes here to help. I have that graph there I'm going to use in a moment. Here are our notes. To bound rho and phi, we're going to project this. We're going to let x equal 0. That projects it onto the YZ axis, right? The other one, to bound theta, let z equal 0. That's going to project it onto the xy plane. All right, so let's give these, do it a few times. All right, so let's let x equal 0. All right, letting x equal 0. On this, that's what we're talking about. We get y squared plus z squared is less than 3. So if I use this is my, let me pull this over here. It's not that important to grab that arrow, but I keep missing it. All right, this projects this onto the YZ plane, and then it has the radius of a square root of 3. All right, so we can actually pull a few things from here. The equation itself, we could grab rho, right? Rho squared is less than 3, which means rho is less than square root of 3. So we actually have the bounds for that. Or we could have used our picture here, right? Going out, the radius stays the same. We also can use this to find phi. Now, phi, remember, it goes from this, I'm going to exaggerate it here, and it goes down. That's going to be phi, all the way down. But if you notice, this goes all the way across, down to the bottom. And remember, phi is caught between 0 and pi. So let's start writing out our bounds. So we have rho, we have phi, and we have theta. Okay, I can see rho. Rho is between the 0 and square root of 3. We also have phi now. If I look at the picture, it goes all the way down. And the only reason we stopped at pi is because that's how phi is defined. Remember, phi doesn't go past pi. Even though this thing goes all the way around, what's going to help us with the all the way around is the theta. All right, so the last thing we have to do is theta. So to find theta, we let z equal 0. So if I let z equal 0, then I got x squared plus y squared is less than or equal to 3. Okay, I can see that that is a circle with square root of 3. All right, we could draw it if we needed to. All right, close enough. All right, this would be on the xy plane and root 3. And I can see by the picture that we have that theta is going to go all the way around, 0 to 2 pi. So it really is helpful. You can imagine how gross this probably could have been, especially what we're about to do for the integrand. We have x, y, z, and we're about to switch it. So let's go ahead and write down our new integral. All right, so let me make this smaller. I need the room. All right, said integral, okay, that is the triple integral over t of x squared plus y squared plus z squared over dv. All right, now we have everything we need. We have theta is between 0 and 2 pi. We also know that phi is between 0 and pi. And then that rho is between 0 and square root of 3. This isn't a 1 integrand because I have something in the integrand. But I know the inside of x squared plus y squared plus z squared is just rho squared. And we know rho is positive, so this is just rho. But then I got to times it by that Jacobian thing, right? That thing that's highlighted there at the top of the screen, which is rho squared sine phi. And now I put my bounds in. D rho, d phi, d theta. If you were wanting to work this one out, this one's not hard to work out. It's actually pretty straightforward because all our bounds are constants. This works out to 9 pi. I would recommend you trying that. Again, this is supposed to make problems easier, not more complicated. Notice what it did with our integral is it took it down to x squared plus y squared plus z squared, and it narrowed it all the way down to that rho, which is going to allow me to work with one variable instead of 3 at a time. I'm trying to think if I could do this in rectangular. It'd be very, very difficult. I'm sure we could find a way to do it. But again, like, this is pretty straightforward, especially once you get your hands on how to do all this right here. Okay.